talking about is the difference between an observational study and a designed experiment. Basically, those are two different ways we might go about collecting data. So whatever our question is that we want to know, like if I want to know, I don't know, how much water a high school student drinks in a day, okay? There's two different ways. What do you think observational means? You observe. So all I do is follow you around, writing down how much water you drink in a day. I'm not doing anything except just watching. What do you think a designed experiment would be? Yeah, something that I set up and I control. So I put you in a room and I'm going to tell you, okay, every time you hear this sound, I want you to take a drink of water or something like that. So you are controlling more of it. So let's look at this example. Did I have, if, so you guys have your example slides, right? Okay. So we have two researchers that want to investigate cancer risk among cell phone users who were followed for up to 21 years. So to do so, they kept track of 420,095 people whose first cell phone subscription was between 1982 and 1995. In 2002, they recorded the number of people who had brain tumor and compared that rate to the general population. They found no significant difference in the rate of the brain tumors between the two groups. So they concluded that cell phone was not associated with an increased risk of brain tumor. Would that be an observational study or a designed experiment? Observational. Okay, all they did was watch and see what happened. They didn't control anything else. Let's look at another one. So this time they want to know if chronic exposure to RF radiation at two different cell phone signals caused brain tumors in rats. So the rats in group 1 were exposed to an analog frequency. The rats in group 2 were exposed to a digital frequency. The rats in group 3 had no radiation. Exposure was done 4 hours a day, 5 days a week for 2 years. The rats in all three groups were treated the same except for this. Okay, and then at the end, they found no significant increases for any group. Is that observational or designed experiment? They broke them into groups, they gave them different kinds of treatments and compared those groups. So when we are trying to decide, I guess we should maybe have some actual definitions. An observational study measures the value of the response without attempting to influence. You're just watching, you are doing nothing to change the outcome. In the designed experiment, the researcher will manipulate the explanatory variable and record the response variable. A lot of times this will require multiple groups. You'll notice this uses a couple of terms that we haven't really talked about: explanatory variable, response variable. So when we are talking about those, the explanatory variable, we're looking to see how much we vary that, the outcome it would have on the response. So for your definition, explanatory variable that is the variable being manipulated. Or controlled. The response variable is the outcome being measured. Okay, so if we think back to those examples that we just did. So the first example, when they were watching the cell phone use and looking at brain tumors, the explanatory variable, they weren't actually manipulating anything because it was an observational study, but what was the thing that would have been the explanatory variable or the controlled variable here? You have an idea? The people? Okay. Specifically, what about the people?
Their cell phone usage.
The cell phone usage. So the people using the cell phone. So cell phone usage would have been the explanatory. Now, did they say, okay, you have to use the phone this many hours a day or anything like that? No, because it was an observational study. But did they make sure that the people they tracked were ones that used cell phones? Yes. So they were only watching the people that used the cell phone. So that was the variable that had to be in place. Then the response, what were they measuring? What was the outcome we were looking at?
Cancer.
Yeah, if they had the cancer or not. All right, what about in this one? So the explanatory variable, the thing being controlled or manipulated, what was that? Yeah, the cell phone again. Now we broke them into groups. We had digital, we had analog, and we had none. But their cell phone usage, the type of signal. And so then the outcome was again the response variable of if they had cancer or not. Okay. Let's look at this one. So researchers wanted to determine the long-term benefits of an influenza vaccine on seniors aged 65 or older. The researchers looked at the records of over 36,000 seniors for 10 years. The seniors were divided into two groups. Group 1 were seniors who chose to get a flu vaccine, and Group 2 were the ones that did not. After observing the seniors for 10 years, it was determined that seniors who got the flu shot were 27% less likely to be hospitalized for pneumonia or influenza, and 48% less likely to die from those things. Okay, so after looking at this, does that mean all seniors should get their flu shots? How swayed are you with people throwing numbers at you? It happens all the time. If you watch the news or you look at anything out there, there's always statistics in it. So if I look at this, okay, if I get my shot, I'm 48% less likely to die from the flu. So is that a good thing? Should everybody get it?
Yes.
Yes? Sounds believable. Everybody thinks so? Got one person shaking their head no. Do you ever? Why? Why would this not be convincing?
Because it might not protect you from something else.
Okay. And so it says nothing else about the other things that could cause you to die, the other illnesses that are out there. So, what we have to be really careful about, and something that we're really going to focus on, is knowing what's a good, convincing statistical argument and what's not. Okay, did I do anything else with these two groups of people? No. I just watched them and I saw did they get it or not and kind of put them in their two groups and went from there. So, is it possible that the people that I looked at that didn't get the flu shot might have had some other reason that led them to be more likely? Sure. What if the people that didn't get it were ones that already had severe illnesses and were advised by their doctors not to get the flu shot because it would compromise their immune system more? Or maybe the ones that got the flu shot, maybe those were people who go to the doctor on a regular basis. They're really health conscious. And do you think being health conscious and going to the doctor on a regular basis would be better for your health? Probably. So can you tell me that they were healthier because they got the flu shot, or was it because they just went to the doctor when they needed to and did all of the other things that they're supposed to do to be healthy? Do we know which is which? No. So there can be other things going on that we're not really aware of. That's what's called confounding. When there are two or more explanatory variables that are not separated. In that situation, the explanatory variable was if they got the flu shot. But I didn't separate that from anything else. I didn't look at any other attributes of these people. I didn't try to make sure they were similar aged people in both groups or similar health practices. I didn't separate that from any other variables. Those variables that maybe had an impact but we didn't consider are called lurking variables. We didn't necessarily think about them, but they could affect the response. Can you give me any examples of lurking variables in that example we just did? What could be some variables that affected the response that we weren't looking at? I've already mentioned a few. Their immune system. You know, did we look at if they had other health issues or not? What about age? We just did 65 or older. Maybe all the ones that got their flu shot were between 65 and 75, and all the ones that didn't were 85 or older. Would that have an impact on it? Sure. Their overall, active. How active are they? That would have an impact on it. So lots of different things. We aren't going to be able to control them all, but we need to be aware. Is that situation, was that an observational study or a designed experiment? Observational. Okay, I kind of looked at them as two separate groups, but did I split them down the middle and say, you get your flu shot and you don't? No. Which is better, observational study or designed experiment? Designed experiment. Just because you can control for more of those lurking variables, kind of like with the rats, they said everything else about their environment was the same in the two groups, except for the one thing they were studying. They had the same food, the same activity, lived in the same place. But it's not always possible to do an experiment. I can't, like medical professionals can't just say, all right, Ella, you get it. Kira, sorry, you don't. We'll see who does better. Like, is that ethical for them to deny somebody the option? No. So it's not always possible to do an experiment, but it will give you better data if you're able. Just a couple more definitions to wrap up for today. A census, if you hear me ask for a census, that's a list of all individuals in the population along with certain characteristics. So maybe I want to know if students in Monroe City High School would favor a 4-day school week. So my census would be a list of every high school student in our school and a yes or no by their name. Are they in favor or are they not? It's everybody in the population. So ideally, if I were trying to decide, I would ask every single student and get their opinion, right? Is it always possible to talk to everyone? No. If I wanted to know every student in the state of Missouri if they favored a school week, 4-day school week or not, that turns into a lot of people and not really feasible to talk to every single one. So tomorrow we're going to focus a lot more on sampling. And what's a sample? Yep, subset of the population, a smaller group that we're looking at. Today I'm just going to touch on 2 terms about a sample. So a random sample is just a random process used to select people. Okay, so it might be I put everybody's name in a hat and I draw one out. Or our prizes in the gym. Mr. Talton puts everyone's name on the wheel and we spin the wheel. That is random sampling. Everybody is equally likely to be chosen. And that's where we'll get into a lot of different kinds of random sampling tomorrow. Where we are going to finish today is on the examples page. We're going to look at 2 more examples. The first one, we are going to create a sample. Okay, so I have a study group with 5 students. I have to pick 2 to go to the board and do a problem. Can you tell me all possible samples of size 2 without replacement? Do you know what that means when I say without replacement? But I'm picking 2 students. I can't say Izzy is the first one, put her name back in, and oh, Izzy is the second one as well. You can't go up twice. So once Izzy's up, it has to be somebody different for the second student. So tell me, what are my possible groups? Can I just abbreviate? Bob and Patricia, or Bob and Mike, or Bob and Jan, or Bob and Maria. Is there any other group that involves Bob? No. Okay, so tell me the next group. Patricia and Mike. Okay, what's the next possibility? Okay. Any other options? No. So that's all possible samples. What is the likelihood of getting Bob and Jan? So how many of these groups are Bob and Jan? 1. Out of how many total options? So there's a 1 in 10 chance that those 2 get selected together. Is that okay? All right. So I want to talk last just about how we could get a random sample from a large group. If you looked in your book, they have like random number tables in the back of the book that you could use to select a sample. I don't really like random number tables. I think they're kind of annoying to use. So I like to use a calculator to do a random sample. So everybody grab a calculator here. Okay, so first, let's kind of create a scenario. Let's say I have a group of 30 students and I need to pick 3 to do a task for me. So what I could do is number those students 1 through 30, and then I have to randomly pick 3 numbers, and then I'll have my 3 students, right? So you could, put their names in a hat and draw them out or something, or we could do something like this. So to start, you have to give your calculator what's called a seed. It's basically just a number to start with in its process of finding a random number. It can be anything. So I'm just going to put 3. And then you see over here there is an STO button. That stores it. So it'll give you a little arrow right above the on button. So you put a number, push store. Now you need to go to math. And you see at the top we have all these options. If we go over, the first one is probability, or all the way over to probability, and the first option is rand. That's what we want. So we picked a number, then we did store, math, probability, and we're going to do random. Okay? If I hit enter, it just tells me that number back. That's okay. We just started the process. So now I want you to go back into math, over to probability, and number 5 is a random integer. Yours is going to look different than mine on those calculators. So it probably says rand and then has a parenthesis, right? So what you do, you're telling it, I need a random number between this and this. So we said between 1 and 30. So you're going to put a 1. Then you guys have to do a comma in between on these calculators.
I'm so sorry. Sorry, I like that one.
Okay, yep, that's it. That's why I was saying yours looks different than mine. So now you're telling it, so you want to go between 1, comma, and 30. Alright, so did everybody get that? So yours will say random integer and have parentheses. You type a 1, type a comma, and 30. The comma is by the parentheses, above the 7.
Why do I have a
You don't have to have parentheses. Yours. Alright, you have the option, if you want, you can go ahead and just hit enter now, and it will tell you the first number. So 29, so I go to whoever's number 29 on my list. If you hit enter again, it's going to give you another number. So you had 26 then, so that's your next person. You need one more person, and so it randomly gives you 3 numbers. You have the option also when you do the random integer 1, 30. You could put a comma 3 after that, telling you you want 3 numbers, and it will give you all 3 at once. Or you can just keep pushing it.
I love this.
Oh, that's interesting. Yeah, this process is not truly random. It has a method of calculating, but it's as close as we can get. You didn't put it. So you want to do between 1 and 2.
Yeah, I wanted to see if it was online.
I guess technically
Sorry.
All right, let's try. You guys want to try one?
Yeah. Well, I'm ready.
Did everybody get this one to work?
Yeah.
Until the very end with the parentheses, but I can delete all of it. Maybe I'll notice.
Okay, so if you want it, I'll create one. Okay. So let's look at this example. The 112th Congress of the United States had 435 members in the House of Representatives. So how could I get a random sample of 5 people? Tell me what I do. Yep. So pick a number, store that as your seed.
Why do we have to do that?
So since we've already stored a seed in the last example, you really don't have to do it again. If you try to generate a random number and the memory has been reset on the calculator, you might get a decimal, and we don't want that. But as long as we put in an integer to start, it should stay there. It shouldn't be a problem. Then we go to math, probability, number 5, random integer. And we want 1, comma, how high do we need to go? 435. If I want all 5 at once, you can just put comma 5 after that. And did it give you 5? Cool.
There you go.
Did everybody get that to work?
Yay.
So that is all I have for today. If you look on Google Classroom, there is a handout posted, and you've got time to work on it.